When we're dealing with a convergent series, then we often can say that the series is going to converge. But we often cannot determine the value that the series converges to. And when we talked about this with the alternating series of the last section, the last unit, we saw that when you had a convergent alternating series, for example, the simple alternating harmonic series, -1 to the n minus 1 over n, that our partial sums, this would be s sub 1, and this would be s sub 2, and this would be s sub 3, and this would be s sub 4, etc. That sequence of partial sums does approach this horizontal line y equals s, whatever that mystery value of s might happen to be. But the most important thing to notice with an alternating series is that those partial sums are alternating between an overestimate and an underestimate. In this case, S1, S3, S5, S sub odd values are always bigger than S, and S sub 2, S sub 4, S sub 6, those are all smaller than S. And both of those partial sequences, right, the odd sequence and the even sequence, those are both approaching the same value just from either side. So the big idea here for the alternating series remainder was that when we took a step to get from one partial sum to the next partial sum, that step was of the size a sub n plus 1, right? So if we had s sub 1, we added a sub 2 to it to get to s sub 2. And if we started at s sub 2 and we're trying to get to s sub 3, we're going to add a sub 3. And if we're going to try to get from s sub 3 to s sub 4, we're going to add a sub 4. So the distance we travel, the vertical distance we travel to get from s sub n to s sub n plus 1 was a sub n plus 1, right? The next unused term of the series. So that's where this whole idea right here comes from, because we know every single time we take a step, whether it's from S1 to S2, or from S2 to S3, or from S3 to S4, every single time we take another step towards that infinite value of n, we always cross over this value to which the series is converging, right? Every single time we take one of those orange steps, we're going to cross over that dotted line. And that's the nature of an alternating series. So we always know that we stepped too far. A sub n plus 1 gives us an overshoot, right? We overshot the value that we're trying to converge to. So that means that the difference between the actual value and the partial sum is always going to be less than or possibly equal to that next unused term. Again, this is just a review of alternating series error bound, which was back in the last unit. And we can kind of summarize that as by saying that the minimum value here, the minimum value is the nth partial sum minus the next unused term. And the maximum value is going to be the nth partial sum plus the next unused term. And we saw that in action a little bit in times past. Now we're going to use a similar idea to talk about the Lagrange error bound. Now the big difference between a series and this Lagrange error bound is that we're now talking about polynomials. And another big difference is that we don't have to have an alternating series in order to use the Lagrange error bound. So that's a pretty big difference because we absolutely positively needed to know that this was an alternating series if we were going to use this concept here. But the Lagrange error bound does not require an alternating series. Okay, but the concept remains pretty much the same. We're going to start with a function f of x, and we are going to approximate that function f of x using the degree n Taylor polynomial. Now, the Taylor polynomial and the original function are not equal to each other. They differ by some other value. We'll call that r. R being the remainder, the difference between the actual function and the polynomial approximation. So we take that equation, we can solve for r sub n, and you can see that r sub n is quite literally the difference between the actual and the approximation. That's what it means when we talk about the error. So you can write that in mathematical notation here, or you could say it in words. You could say the function is equal to the approximation plus the remainder, or the remainder equals the function minus the polynomial approximation. All right, so again, pretty much exactly the same idea we had up here, where we had an approximation s sub 1 or s sub 2 or s sub 3. We have those approximations, and we're talking about r being the difference between the approximation and the actual value. Okay. All right, so now we look at this business right here. This is a formula that you're not going to understand right off the bat. So don't try just yet. Just kind of start absorbing it. So again, this r sub n right here in the orange, that is again your error. Now we're going to stop worrying about whether it's a positive or a negative, and we're just going to go ahead and say the difference between the two. We'll take the absolute value of it, so it's always going to be positive. The difference between the approximation and the actual function. So don't worry about the fact that up here it was the function first and the polynomial second, and here it's the polynomial first and the function second. It doesn't matter because we've got those absolute value bars here. So we're not going to concern ourselves with whether this is an overestimate or an underestimate. We're just going to talk about how there is some sort of difference between the actual value and the approximation. And if you look at that mysterious last bit here, this part with a z and an x and a c and an N, and an F, lots of letters floating around in here. Hopefully you realize that this looks very similar to the next unused term of a Taylor polynomial. If you recall, Taylor polynomials are built by taking the f of, I guess it would be f of c, right? Plus f prime of c times x minus c, right? And then you take the second derivative, evaluate that at c, and then you take x minus c, x minus c raised to the second power, and then we don't forget to divide by 2 factorial, and we keep on going until we get to the nth term, and we say that's the nth derivative of the function evaluated at c, divided by n factorial times x minus c raised to the n. That's what t sub n of x equals if you're centered about x equals c. Okay, so I want you to kind of look at this and this, the highlighted thing and that last term. You'll notice the n changes to n plus 1. You'll notice the n changes to n plus 1. You'll notice the n changes to n plus 1. This looks like the next unused term of the Taylor polynomial. The only difference is we're not going to look at the next unused term evaluated at the center. We're actually, because if we plugged in x equals c, we're just going to get a 0 over here, and that would always give us 0. But we have to pick some value z. What in the world is z? Well, it's a number, and we'll talk about its meaning in a moment. But for now, just know that it's a value that we need to be able to find. Actually, I take it back. We're not going to be able to find it. More on that in a moment. So anyway, you'll look down here, you'll see, oh, wait a second, this looks kind of familiar. This is what I just wrote up there. If a function f is differentiable through n plus 1 derivatives in an interval containing c, then we can build that Taylor polynomial up to the nth term, and then we don't say that the we don't put the n plus first term here. We have this mystery remainder value, right? Again, this is that difference between the actual and the Taylor polynomial approximation. Okay, so this would be, again, that r being the remainder, the leftover stuff. And what we're saying here is that the remainder is going to look like that next term in the Taylor polynomial, except we don't know what value to evaluate the n plus first derivative at. This mystery value z is definitely going to be some value, and that value must be z must be some number between x and c. All right. So with this intro to the Lagrange error bound, you're not meant to quite understand exactly how to use it. Uh, all I'm trying to do right now is to introduce the idea that we are trying to figure out not exactly what the remainder is, but maybe what it's related to. Okay, and again, go back to the alternating series error bound and notice that it has to do with the next unused term, and again with the Lagrange error, that is also going to be related to that next unused term.